Hi, everyone. My name is Anran Wang from the University of Washington. And today I'll be talking about the kinetic cities and smart fabrics. This is a joint work with Vikram Iyer and Vamsi Talla, advised by Shyamnath Gollakota and George Smith. So let's start with the vision of kinetic cities. As you walk around the city, you can see posters and signs at the side of the street showing bands and concerts, and advertising sales, and even showing public service announcements. But what if we could actually interact with them? What if we could hear the music from that band as we pass by? The challenge to do this is that we need the posters to communicate rich multimedia data. A second related vision is smart fabrics. The clothes we wear open up all kinds of opportunities to integrate everything, including the interaction devices and health sensors. Imagine a shirt that could monitor your heart rate and perspiration. Again, what we really need is the ability for the fabrics to communicate. So the key challenge in both these visions is that radios are unsuitable for these applications. Playing music continuously from a poster using either Wi-Fi or Bluetooth consumes so much power that a coin cell battery cannot even last for 12 hours. Smart fabrics have a different problem, which is that everything, including the battery, should be flexible. However, the flexible batteries in the market cannot even run a normal Bluetooth or Wi-Fi radio. So instead of radios, in this paper, we use backscatter communication. Let's see what we need for backscatter first. We need an RF source that generates the signal, and our poster that can backscatter, and the receiver that can decode the backscattered signal. Since you don't want to carry around the radar everywhere, the first requirement is that we want the ambient signal to be everywhere around us. So that includes Wi-Fi, Bluetooth, and television, and FM signal. The second requirement is that we want the signal to be available in outdoor environments, so that eliminates the Wi-Fi and Bluetooth. And the last requirement is that we want the receiver to be already equipped in our phones and cars, so that it rules out the television. So if you think about it, what we need to do is to backscatter the FM radio signals. In this work, we introduce FM backscatter, which enables wireless communications using reflecting ambient FM radio signals in outdoor environments. The backscatter signal can be either decoded in our smartphones and even your cars. At a high level, if we look at the different FM bands in the spectrum, we first identify the strongest FM radio signals. In this case, the strongest signal is at 94.9 FM. Next, what we are going to do is to find the nearest empty band. In this case, it's 95.3. And we can use backscatter to shift the ambient signal to that empty band. Finally, we want to use our posters to generate the signal to superimpose to the existing signal. So in summarize, we are superimposing our own data on top of the FM signals. Here are our own contributions. We show for the first time that ambient FM radio signals can be used for backscatter communication. And using this, we enable everyday objects to communicate to your phones and cars, consuming as little as 12 microwatts of power, which is compatible with flexible batteries as well. Finally, we also built the first prototype of a smart poster and shirts that can tow to your phones and cars. To see how this works, let's welcome Vikram to the stage and show you a demo of our smart poster prototype.
Hi, everyone. My name is Vikram, and I'm going to show you a brief demo now of how our system actually works with this smart poster here. We've got 3 components in our system. The first is an FM transmitter that I'm holding right here, and this is simulating, the FM towers that would be outside because we don't get very good FM radio coverage in here. The next thing that we have is our poster with actually an antenna integrated on the back with copper tape. And this is actually just as flat and flexible as the paper that this poster is printed on. And the last thing that I have here is just a normal smartphone. And this is acting as our FM receiver. So to show you how this works, I'm first going to show you the original FM radio station. And we're actually, let's see if I can get the audio to play on here. So here, in the background, we're just transmitting a news program.
Says Republicans are in a bind because whatever happens on their watch.
So that's what's coming from from our transmitter here. And now, if we go to the next radio station over at 101.1, we can actually hear the music that's coming from this poster. So that's just a quick overview of something that we can actually do with this system. And now I'm going to go into some more detail about how we actually do this. I'm going to split this up by answering 2 main questions. The first is, how strong are these ambient FM radio signals that we're backscattering? And the second is, how do we actually encode our own information on top of these signals? Let's start by looking at the first question, about the strength of ambient radio signals in real outdoor environments. To answer this, we actually did our own survey of radio signals around the Seattle area. We did this by splitting up the entire city into a grid, and we drove through each of those squares and measured the signal strength of FM radio. We actually covered some pretty complex terrain here, where in downtown we had lots of tall buildings, and in other areas, for those of you who are familiar with Seattle, we had lots of hills, ups and downs. So here are our results, where on the left we're showing a heat map of the data that we measured. And on the right, we have a CDF showing the same information. Now, the thing to notice here is that the median FM signal power is actually about minus 35 dBm. And the minimum that goes down to is about minus 55 dBm. And the other thing you can see is in our coverage map on the left, we actually get pretty consistent radio coverage across the Seattle area. To give you some context for what these numbers really mean, this ambient FM that we measured is actually a lot stronger than your typical Wi-Fi signals that are often minus 60 dBm or even less than that. So at this point, I've shown that FM signals are actually pretty strong in outdoor environments. So the next question is, how can we actually encode our own information on top of them? Let's look at this in a little bit more detail. So let's start by looking at a normal FM transmitter and receiver pair. An FM transmitter sends out a signal that looks something like this. Now, the omega term within this radio signal corresponds to the frequency that it's being transmitted at. So that's, say, like 94.9 FM that you would tune into on your radio. The other component here is this SFM, is the sound signal that's being encoded in the radio transmission. Now, if we look at what our receiver actually decodes, it's not the whole radio signal, but all it gives us at the output is just the sound signal that we hear as audio. So now, let's see how our backscatter device fits into all of this. The way the backscatter works is backscatter changes how an antenna is reflecting energy, in this case from our FM source signal. And we do this by toggling a switch that's connected to our antenna. Now, if we control that switch with the signal B, what backscatter does mathematically is it multiplies that signal by the original FM signal. The thing to note here is that all of this is happening in the RF domain on the radio signals that are going out over the air. The problem, though, is if all we get at our receiver is the audio signal, and now that we're doing this complex multiplication, it's unclear what kind of audio we're actually going to get. So the key challenge is we need to find a way to transform these operations in the RF domain into something that we can actually hear as audio. Our solution to this problem is actually really simple. What we do is we create a backscatter transmission with the exact same structure as a normal FM radio transmission. Let me show you how that works. If we create a backscatter signal that looks like this, you can see the structure is just the same as our normal FM signal. But the difference here is that we're actually encoding our own sound signal, SB, which is whatever audio or sound we want to transmit. Now, if we just think about the properties of multiplying two exponentials, what we actually get is the sum of these two audio signals. Now, the thing is, this whole thing is actually just like another FM radio station. So what our receiver is going to decode is actually that sum of the two audio signals, where we've got our original FM station and the music that we're backscattering overlaid on top of that. So what I've shown here is how we're transforming multiplication that happens in the RF domain with backscatter into an addition operation on the audio signals. So we show a few other improvements on this basic technique. And the first is we demonstrate how we can reduce the amount of the background sound that you hear from the original FM transmission. And the way that we do this is by leveraging the stereo mode of FM radios. The second capability that we show is that we can actually transmit digital data by encoding it in this audio stream that we send. Specifically, we use FSK modulation at frequencies between 8 and 12 kilohertz. And because this is a little bit higher than most human speech that might be in the background FM signal, we can actually send data pretty reliably with this method. We do experiments and show that this whole system, or both of these techniques, actually work at distances of up to 12 feet. So next I'm going to talk a little bit about our actual prototype, which we have a picture of here. This is something that we just built with off-the-shelf parts like a Raspberry Pi and an FPGA. And you might be thinking now, this looks a little big to stick on the back of a poster or something. But the thing to remember is that with a backscatter system, we can actually create this whole thing that I'm showing on the left as a custom chip that's less than a millimeter square of silicon. And we show in our paper that our simulations for this design consume less than 12 microwatts of power. So once we build this custom chip, that really enables all of the applications that we've been talking about. The last thing that I'm going to show you is a couple of the proof of concept applications that we actually built. The first is we show that posters can not only talk to our smartphones, but also to FM receivers that are built into cars. Here's a quick video showing how that works.
From APM Reports. Just a note before we start, this program includes content that some listeners may find disturbing.
Now, another thing that I want to comment on this demo is we noticed that the FM radio receivers in cars and their antennas are actually a lot better than the ones that are built into phones. And when testing this system with cars, we actually got an improvement of our range and could get it to work up to about 60 feet. Now, the fact that we're able to interface directly with cars is really great, and I think this is something that will really help to enable this vision of connected cities that Anran talked about before. The other prototype that we built was a shirt that actually has an antenna integrated into it. And this is made out of conductive thread that's sewn directly into the fabric. I'm actually wearing this shirt right now. Let's see. So just to show you and actually point it out, it's hard to see, but there are these lines here that are made of conductive thread and actually form the antenna pattern. And we showed that by using this prototype, we can actually send data up to 1.6 kilobits per second. And this still works actually, while wearing this shirt, while walking and running around, things like that. So to conclude, we've shown the first demonstration of a backscatter system that works with ambient FM radio signals outdoors. To take a step back, our group has done a lot of work on backscatter over the past few years. And this is yet another demonstration of the capabilities. And we hope that in the coming years, that we as a research community can continue to explore backscatter and eventually make sure that backscatter systems can achieve the same rates, spectral efficiency, and ranges that can compete with traditional radios. Thank you.
Any questions?
Yeah, this is Rick Farrow. That's pretty fascinating. So essentially what you're doing, say with the poster, is you have a connection to ground that you modulate. You modulate the connection to ground, and that creates the FM signal, right?
Yeah, or we're changing the impedance that's actually connected to that antenna.
Impedance. Okay. Yeah. Okay. Very fascinating. Thanks. And that's why, of course, it takes very little power, because essentially it's just the relay
exactly,
or the switch.
Exactly. So all we're doing that we need to consume power in this system is, to actually turn on and off that switch and whatever control logic which is actually playing.
Sure. Okay, thanks.
Could you also put these transmitters in cars? That is, instead of the poster or the shirt, could a car be transmitting too? Could you build a car-to-car network using this sort of a system? What would be the challenges? Of course, which channel you send it to, that's going to be variable.
There are a couple of challenges that we'd have there. And the first is we haven't done many tests with moving transmitters and receivers. So that would be something to look into. But it's definitely something that you could actually integrate into a car.
But they have good FM transmitters and 60 feet,
exactly.
Right? They have good FM antennas. You'll have to add the transmitter, but it could.
Yeah, and the nice thing is in a car, again, just like the applications that we've showed, you're really not constrained in terms of space for putting a good FM antenna.
Right.
So.
Yeah, and they are actually pretty very small FM transmitters that can plug into the cars in the market. And you can use it as a transmitter, actually.
Yeah, that'll be cool. Let's thank the speakers and all the speakers in this session again.